Okay, Gen Chem kids, we are going to learn a little bit more about the periodic table today. If you have a paper copy of the periodic table in your notebook, I would advise you to get out some crayons or some markers or some colored pencils because we are going to be marking things up with color today to help us differentiate different things on the periodic table. Okay, so the first thing that we want to do is to put down some definitions. So you should be here at chapter 4, the periodic table. I think it's about page 47 in your workbook. Okay, so introduction to the periodic table. This is the periodic table that we have modern-wise. You'll notice that the last couple elements here are not filled in because we just really named them about 4 years ago. So the periodic table that I have in the front of the room is more recent than this, and it does have the names for those in there. Okay, so a quick review. Metals. We want to think about where the metals are on the periodic table, and we also want to think about some of the properties that metals have. So let's write in the properties of metals. Okay, so metals are solid at room temperature. So they're solid at room temperature. Now, there's one exception to that rule. The exception there is mercury. Mercury at room temperature is a liquid. Okay, they're shiny. Oh my gosh, I can't spell today. Do you guys ever have days where you just can't spell? They're shiny. They're good conductors of heat. So they're good conductors of heat and electricity. They also are what we call ductile. Ductile means that I can make a wire out of metals. And we've seen wire made out of metals, copper wire, silver wire. And they're also what we call malleable. And that means that I can make a thin metal sheet out of metals. So I can pound lead or iron or copper or anything into a thin little little metal sheet. Okay, the next thing we want to talk about is our nonmetals. Okay, so our nonmetals have different properties than metals. So they're almost the opposite. We have some of them being solids, some of them being liquids, and some of them being gases at room temperature. So they're all 3 states at room temperature. So we can't really categorize them this way, but they're definitely not shiny. In fact, they are dull. They are really dull. They don't have any shininess or any luster to them, and they're brittle. So if they are solids at room temperature, they're brittle. That means they break easily. If I hit them hard, they'll break, they'll snap, they'll shatter. And they are not good conductors. In fact, being not a good conductor is called an insulator. They're insulators. Not good conductors of heat or electricity. So they don't really do heat or electricity very well. Okay. Metalloids. Let's get another color here. Metalloids are actually a a little bit in between metals and nonmetals. So they have properties of both metals and nonmetals. Okay, so they can conduct electricity, but not super well. They're not great conductors. They're not great insulators. They're not super dull, but they're not really flexible or malleable either. So they're kind of in between. Because of that, because they can conduct electricity, but you can kind of shut it off too, metalloids are used as they're used as semiconductors. So they're, I can't write very well. So they're used as semiconductors. And if you know anything about the computer world or the electronic world, every single thing that has a chip in it, a flash chip, a hard drive, or whatever, like our phones use flash. So the chips that we have for our phones are made out of semiconductors. Usually they're made out of silicon. Okay? So let's put those on our periodic table first, and then we'll dive into the rest of these. So we're going to I'm going to first put in the line between the metals and the nonmetals. So I'm going to make this line really thick. Okay? Now the line between the metals and the nonmetals is what I call the staircase, and it always starts below boron and just makes a stair step down the periodic table. Okay? So this line tells us where the metals are versus the nonmetals. Okay? So to the left of this line, we have the metals. And to the right of this line, we have the nonmetals. Now, we do have one exception to that rule. Our exception to that rule is hydrogen. Okay? So hydrogen is a non-metal. Okay? So that's our one exception to that rule. Now, I also told you that we would put in the metalloids. Now, the metalloids that are kind of having properties of both the metals and the nonmetals are going to be right on that line. So I'm going to highlight the metalloids. The metalloids are boron, silicon, which we use to make computer chips, germanium, arsenic, antimony, and tellurium. Those are our metalloids. Now notice that they follow exactly the line of the metals to the nonmetals. So you would expect the elements that have the in-between properties to be right on that line. Okay, let's go and define some more groups and some more things that we want to talk about. Okay, we have a special group of metals called the alkali metals. And this is group 1. Now, the alkali metals, they're shiny. They're very light in that they are not dense. In fact, some of them, like lithium and sodium, can actually float on water. They're called alkali metals because in British English, not American English, but in British English, alkali means base. So if we put these metals into water, they will react with water and they will turn that water basic. Okay? They react with water. In fact, I might list a video, I might link a video with this to have you look at this. They react with water so well that the further on you go down that group, the more reactive it is, and it gets to be quite dangerous. Okay, so the alkali metals are group 1. So let's highlight that really quick. And let's find a color that we want to use. So let's use yellow. Okay, so our alkali metals, they're group 1. So remember, groups are our columns on the periodic table. So our alkali metals are group 1. So I'm going to highlight that right here, showing that I've made the alkali metals yellow. Okay. Now the alkaline earth metals are a little bit different. Actually, let's do yet another color here. The alkaline earth metals are group 2. Okay, they are also shiny. They're shiny, and they're not super dense either. They don't react nearly as strongly with water, but they do react pretty well with a lot of what we call earth things, and they make a lot of the compounds that we use every day. So I'm going to highlight the alkali earth metals in a different color. Let's choose yet another different color. Okay, I'm going to put these guys in magenta. Okay, so the alkaline earth metals are group 2. Now remember, from previous groups are our columns in the periodic table. So our alkali earth metals are group 2. Halogens are another group. So our halogens are group, oh my gosh, I don't want it that thick. Let's erase that, and let's get it to be a little bit thinner. Okay, our halogens are group 17. Okay, now you might have heard of halogen lights. We use halogen to create lights a lot because when they have electricity through them, they resonate, they burn so brightly. The electrons will actually give us quite a lot of the color spectrum. So a lot of the lights that you use for headlights on a car or whatever are going to be filled with halogen gases. So let's highlight the halogens on the periodic table here. And they're group 17. Okay, I'm going to put them in this kind of lavender lilac color. The halogens are right here. So we have fluorine, chlorine, bromine, iodine, and acetylene. And we use fluorine, chlorine quite a lot, actually, in everyday. Fluorine we use for strengthening our teeth. Our toothpaste and our water are fortified with fluorine to strengthen our teeth enamel. Chlorine we use a lot for cleaning. It's used in a lot of applications. Okay, and iodine is a trace element that we all need to have to live healthfully. If we don't have enough iodine in our diet, we get a disease called goiter. All right, next thing that we want, I want to highlight that we did the halogens in this lilac color. Okay, noble gases. Noble gases are group 18. Now, funny thing, they're called noble gases based on nobility. Wonder why it did that. Okay. So if you've learned anything about European history, the nobility did not ever mingle with the common people. And the reason that noble gases are called noble gases is they are unreactive. They do not react with other elements. They do not react at all. They don't mingle with any other element. And so because they keep themselves very separate from all the rest of the elements on the periodic table by not reacting, we call them noble gases, kind of to reflect the snootiness or the aloofness that nobility used to have. So let's put that on there. And let's do yet another color for them. So I'm going to put them in green. Okay, so our noble gases, helium, neon, argon, krypton, xenon, and radon. Okay, and we use a lot of the noble gases for different applications. We'll make signs out of them. Radon is actually a radioactive gas that causes lung cancer, and we have a fair amount of it here in Utah. So noble gases, we will put that here. Okay, so here we go. Let's do some more things on the periodic table. A group. Now, if I remember a group, our groups are the columns, okay? These are the columns, okay? The up and down on the periodic table, okay? Now, if we count them, we have 18 groups. There are 18 groups on the periodic table. So let's count that on the periodic table. So if I count over 1, 2, 3, 4, 5, 6, and so on, we have 18 groups on the periodic table, okay? Now, the reason that they are called groups is that the elements in those columns have very similar physical and chemical properties. They have similar chemical and physical properties. Back in the day when I was in high school, these guys were also called families because of the similarities. I don't know about you, but I look very similar to my mom and my dad. I look like a mixture. And my kids look very similar to me. So because we have similarities, they used to call them families because these elements all have similarities. Now, we're going to get into this a bit later, but they all have their similarities of their chemical and physical properties because they have the same number of valence electrons. So they have the same number of valence electrons. Now, valence is just a fancy word to say outer shell. So the outer shell of these atoms all have the same number of electrons. Okay, next thing, we want to talk about periods. Now, on the periodic table, we are talking about rows. Okay, so the period are the horizontal rows. Okay, now our rows have to do with energy levels. Okay, And you'll see that we have 7 of them on the periodic table. So let's go and label those on the periodic table. Okay, so we have 1, 2, 3, 4, 5, 6, and 7. Now, a lot of kids are going to be like, well, wait a second, what about these down here? Now, these down here, if you remember, look at these numbers right here. These fit right in between here. Okay, so those are actually part of period 6. And these right here are actually part of period 7. Okay? The reason we don't put them there is it would make the periodic table so wide that it would be really, really unwieldy to use. Okay? But in reality, those should be there. Okay. Now, the transition elements. The transition elements are what we call the transition metals or transition elements. Now, these are the elements that are groups 3 to groups 12. So these are metals. They are metals, and they are groups 3 to 12. And they're usually what we consider the normal metals. There's iron in there, there's copper in there, there's silver and gold and zinc. All the things that we normally think of as metal are in that transition elements group. Okay, so let's put this here. Let's see. Let's find another color. Okay. Let's use this rose pink. Okay. Transition metals are right in here. Okay. So all of these, and I'm not going to color it in really nicely. If you want to take the time to do that on your sheet, you can. But I'm not that particular. Well, I guess I am that particular because I'm going to do it anyway. So yeah, you get to see my OCD in action here. Okay, so that is the transition metal block. Okay. So the transition metals. Now the lanthanoids and actinoids, they have a different name of a group that they also go by. So we want to name that other group. Together, the lanthanoids and actinoids are also called the inner transition metals. Okay, so the lanthanoids are down here at the bottom of the periodic table. So the lanthanoids are numbers 58 to number 71. Okay, they're the first row on the bottom. So let's get that in here. Let's change a color. Let's use the sky blue. Okay. So the lanthanoids are right here. You'll also notice that on some periodic tables, they will actually pull the lanthanum down here and have it be part of the lanthanoids. Okay, and then you probably guessed the actinoids are the same thing, but one row down. So let's change the color here. The actinoids, we're going to put this gray here. The actinoids are just the next level down. Okay. So the lanthanoids and actinoids right there. So let's color code this. I put this soft gray here, and I put the soft blue for the lanthanoids. Okay, so the actinoids are numbers 90 through 103, and they're the second row on the bottom. Okay, so those are called the inner transition metals, and we use the inner transition metals for a whole bunch of things. They're really useful, especially probably the thing that you're used to seeing them more, things that make your screen and the colors so vibrant on your phone screen. Those are all done with the inner transition metals, those bright colors. When we put electrons through them and excite the electron field in them, we get these bright, vibrant colors. So we use a lot of inner transition metals in manufacture of electronics, anything that has a bright screen. Okay, the next thing we want to talk about is the periodic law. Okay, so when we talk about periodic law, we are talking about a law that Dmitri Mendeleev gave when he proposed this periodic table. Now we're going to get into the history of when he proposed the periodic table and how wonderful it was, but this is one of the laws that he used to propose it. He noticed that if he put the elements in order of their masses, he saw repeating patterns over and over again. So that repeating pattern, he called it periodicity, meaning every period, every so often, he would see the same pattern over and over again. So periodic law is the chemical and physical properties So the chemical and physical properties of the elements recur or repeat periodically. When elements are arranged according or in order of atomic numbers. So if I do and I arrange the elements in terms of ascending or getting bigger or increasing atomic numbers, I will see the same patterns repeating over and over again. Now remember, when Dmitri Mendeleev first did this, he didn't do it according to atomic number that we did. It was first done with mass. First done with mass. And we've realized now that it's not the mass that determines the element, it's the number of protons or the atomic order. or the atomic number. So we do it with atomic number now. Okay? Now the octet rule. Octet, those of you who are in music, you'll realize that music is much done with octets. Octets are eighths. You can do an octet in terms of the signature. You can do an octet in terms of the scale, in terms of a chord. You can also do an octet in terms of the number of a group. Okay? So octet just means that I have 8 of something. Okay? So the octet rule in chemistry is super, super important. And in fact, there was a chemist in England that came across proposing the law of octaves. That's why an octave is called an octave, because it has 8 notes in it, not counting the half notes. And he noticed also, like Dmitri Mendeleev, that these patterns kept repeating every 8 elements. But you know what the Royal Academy of Sciences did in London to that poor fellow? They left him right out of there. They're like, there's no reason to do music in chemistry. This is science. This is not women's parlor tricks. So they thought it was just ridiculous that he would put music and create a metaphor with music. But he was right. Okay, electron transfer or sharing. Okay, so when we get into these electron configurations, we'll see that eventually a lot of these elements are going to want to transfer, meaning give or receive electrons from each other or share electrons with each other. And it happens. So an atom can acquire an octet or 8 electrons in its valence shell. And remember, valence just means outer. So we're looking at the outermost shell of electrons on the atom, okay? And you'll notice, once we get into this configuration, that 8 electrons in the outer shell gives it a noble gas configuration. So i.e., noble gas configuration. Okay, there's something very, very stable about that noble gas configuration. Okay, so let's talk about the periodic table a little bit. And I will link a video to you. Dmitri Mendeleev, probably one of the most amazing scientists I've ever run across. Russian scientist, grew up very poor. He was the 17th child of this family. He was the youngest. His dad became blind when he was young. His mom had to run the family, and she ended up, the glass factory that she was running, and it ended up burning down. So they were very poor. His mom finally found him a position at the institute in St. Petersburg so that he could study. And after she dropped him off at that university in St. Petersburg, she died pretty soon after. So Dmitri Mendeleev was essentially an orphan by the time he was about 13 or 14 years old. He found studying science was his jam. He loved it. So this is what he first came up with for the periodic table. Now, when he did this, he took the elements and he arranged them according to their weights. And they exhibit a periodicity, meaning a repeating pattern of properties. So you'll notice that the periodic table that he came up with is very different than ours. But let's take a look at this first column. He's got hydrogen, lithium, sodium, and potassium. Let's look at ours really quick. Come on, scroll down for me. We also have hydrogen, lithium, sodium, and potassium right here. So it does match up, but it's not nearly the same as what we have now. Let's go back to Mendeleev's table that he proposed in 18. Oh my gosh. Why does my stuff do this? Okay, so his table that we have. My goodness. This is making me quite mad. Okay, the other thing that's really important about this table, do you see this? That is actually the brilliance of Mendeleev's table. He left blanks. He said, there are elements that we have not discovered yet. And because of where they are in the periodic table, I can tell you about these elements. These elements will have this kind of a mass. They will react this kind of a way. They will have this kind of a density. So based on where things are in the periodic table, Dmitry Mendeleev could tell you what properties these elements should have just based on this periodicity or the repeating patterns that he saw in the periodic table. Now, there's one more thing that I want you to know about this periodic table. Now, Dmitry Mendeleev published this in 1869. There was another scientist that also published a periodic table the same year, and his name was Lothar Meyer. And I just spelled his name wrong. Lothar Meyer. Okay, this guy is German. And in German, TH are like a hard T. So his name would be pronounced Lothar Meyer. He also published a periodic table in 1869. But the reason that Mendeleev gets credit is Mendeleev was working on this for 13 years. So Mendeleev really could have started publishing in 1856. Okay, so Mendeleev was first in publishing, and he was also the one that was able to understand the periodicity of this a lot more than Lothar Meyer. Okay, so hopefully you have a great day, and we'll talk to you later. Bye.